One of these days I'll see one of you giving a keynote at a networking conference, even if that wasn't your favorite class. So hopefully by the end of the talk I'll convince you that there are some exciting things to do at the boundary between networking and programming languages. I stumbled into this. This has been a long journey for me, actually. I've been working in this area of network configuration for, I would say, 10 to 15 years, dating back to when I was working on my PhD thesis. And for those of you who don't know me, my work basically focuses on designing tools, techniques, and protocols to help network operators run networks better. And what that has meant for many, many years is helping operators deal with very low-level, device-specific configuration languages and so forth, things that none of us like to think about, least of all you. It turns out that basically configuring these networks it turns out to be a very hard task. For many, many years, network researchers spent most of their time thinking about protocols. But when I started getting into this area quite some time ago, we started to realize that a lot of the interesting behavior of networks and of the protocols actually was not so much in the definition of the protocols, which you can read in standards documents, but actually how operators were configuring those protocols. So a lot of the behaviors of a network that determine where traffic can and can't go, how it's prioritized, the encoding of business relationships, and so on and so forth, actually is all in this sort of very low-level, device-specific, often proprietary vendor configuration, device configuration stuff. It turns out actually that configuration turns out to be not such an easy task. And as I discovered, you can get a PhD thesis trying to help network operators make sense of the mess. And it's hard for a number of reasons. One is that there are high-level tasks that network operators are trying to achieve. Often these things are trying to separate different portions of the network, so you may not want a particular group of users in an enterprise network to have access to the payroll or the HR part of the network. You may want to defend against attacks. You may want to prioritize certain types of traffic, say video conference traffic or streaming over some other types of traffic and so forth. And you'd like to be able to just say that like I was just telling you. But it turns out that a lot of those higher level tasks are realized through very low-level commands and often scripts that sort of are wrapped around those low-level commands. And as it turns out, that just makes the whole endeavor very difficult for operators to understand. Now, often, as we write software programs, we think about writing a program and then maybe it runs in a distributed way, but we're not writing a little bit of the program over here and a little bit of program over there and repeat 500 times, right? But that's actually what's going on with network configuration by and large. Is you've got, let's say, take a very large backbone network like the transit providers we might be familiar with, AT&T or Comcast or Google or what have you. A lot of all these organizations run very large networks, and the number of network devices is quite staggering, actually. If you just take the routers that forward network traffic, any of those networks that I mentioned would have something like maybe 500 routers. Once you start adding other things in, like firewalls, middle boxes, load balancers, etc., then you've got a lot of devices in the thousands. And the trick here, the thing that makes it so painful is that often these devices are configured independently, right? So an operator will go configure one device, put some access control rules or firewall rules on a particular firewall, or they might configure an intrusion detection device, or they might configure a load balancer. All that's completely separate from the routers and switches that are establishing topology and so forth. And so this becomes extremely hard to manage, right? If you sort of want to ask even simple questions like, does a packet, a machine that's sending traffic from a particular point in the network, is it even going to get to, from A to B? Turns out to be a very difficult question. Even things like, do we get a stable topology? That's another seemingly simple question that actually turns out to be very hard to get to the bottom of. Okay, so you could stop there, and I actually, when I did my PhD work, you kind of stopped at the second bullet there and said, okay, well, we can make a little bit of sense of this. And I did this for sort of one protocol, right? And I did it in the sense of like, here's a snapshot of the network configuration across hundreds of routers across a backbone, and you can sort of get some idea of what the topology is going to be, where the traffic's going to go, if you make, somewhat strong assumptions. But unfortunately, things change, right? There are failures. Links fail. Switches fail. Routers fail. There are attacks. There are changes in traffic dynamics and so forth. And what this all means is that a network operator who spent some amount of time trying to basically get everything right now has to change everything, right? Or change some things. And first question, of course, is, was the initial configuration right to begin with? And maybe, hopefully, is sort of the best that we can get. And then now you've got to go in and change everything. Well, is the change gonna introduce any errors? Well, we don't know if anything's right in the first place, so I don't even know if we should even ask that question. But here's the other kicker, right? Nothing is really checked for correctness, right? So how does sort of testing and verification work? Well, it's sort of like changing the wheels on a car as it's rolling down the highway. Testing, well, let's just sort of make some changes, and let's hope that those changes don't actually induce any unintended or unwanted side effects, and let's hope that whatever I did, even if it appears to be right, isn't going to cause some catastrophe later when a failure occurs and some latent bug is uncovered. Okay, so hopefully I've convinced you that there's some work to do here. We have been working on this for many years, as I said, and I'll tell you about today, as the intro noted, there's some new trends that are actually creating some hope here. I'll tell you, actually, when I started working on this, my thought was this distributed low-level configuration stuff is really messy. Really, we should have some kind of new language to help operators do this better. And at the time, the feedback I got on that, and this was probably 10 years ago, was a little more than 10 years ago, was operators kind of know their thing, right? They're Cisco certified engineers. There's sort of this ecosystem around that. Everyone sort of knows Cisco iOS, or if you're lucky, they know some other configuration language from an also-ran vendor. You can come up with a new language, but no one's going to use it. And I actually think that within the last 5 years, that whole story has changed. I think we can now say, actually, the tides are turning. As the title of my talk sort of alludes to, I teach a MOOC on this topic, and contrary to what you might think, what you may read about the demographics of MOOCs, the demographic of my MOOC is largely 30 to 50-something year-old network engineers at Cisco who are looking for basically to keep their jobs, essentially, I think, or to basically change the world, and I think that's now happening. If I haven't convinced you, basically, that something's going on here, maybe this will actually illustrate a little bit more. So as part of that MOOC I teach, actually, as I mentioned, a bunch of network operators take the course, and I asked them a few questions about how they configure their networks. Okay, so 20% of these operators make changes to their network more than once a day. So this is a survey of several hundred operators, by the way. Okay, so okay, another sort of interesting statistic. Most of them are never completely certain that when they make a change, right, that they're not going to introduce some new bug. So they really have no good way of sort of figuring out that they're not going to introduce a mistake when they do that. Another fairly, among that as well, fairly large fraction of those operators are concerned that, well, they're changing something that has to do with some new functionality or something they need to change, but they're not even sure that when they make that change, they're not going to break something that's like already working. Right? Okay. So, I sort of reflected this back to the group after I did this survey, and took some feedback. And one of them said, "You should track down the other operators who say they're certain what's going on because they're probably lying." So, we have some opportunities on our hands to fix some things. As I mentioned, I think this was incredibly difficult for quite some time due to the sort of nature of how configuration worked. And I don't think if it weren't for this particular trend that I'd be standing here in front of you today, I think we'd probably still be limping along even more than we are. You may have heard this buzzword, and it means a lot of things to different people, depending on who's trying to sell something. But let me sort of try to de-hype it for you. So there's this paradigm called software-defined networking, or SDN. And the best way, I think, to describe it in one slide is with this figure that I've shown here. So as I described earlier, a conventional network kind of looks like this. You've got a few more routers than this, but the main idea is that each one of those routers or switches is running its own control logic, right? So there's an integrated stack on that device, and an operator typically is going to write configuration for every single one of those routers and switches. Now, it's not quite as bad as that sounds. They have, as one of them described to me, a 10,000-line awk script that can sort of do some magic and push things out to those, but that should give you an idea of where the conventional networks were. So what SDN does is basically recognize that, and this is actually an insight that I should also credit to my colleague and mentor Jennifer Rexford, who, when we were working on the problem over here on the left and trying to ask these sort of what-if questions, right? What is this network going to do? We sort of realized that was a really hard problem. If you sort of look at these underlying configurations and say, well, what's this network going to do? Where's the traffic going to go? Are we going to have loops? Are we going to have oscillations? And you can kind of back out what the thing on the left is going to do with inference and making a lot of assumptions. But wouldn't it be better if we could just kind of make it so, right? And that's sort of where SDN comes in, right? Is let's recognize that these routers and switches, they have a job to do, which is to forward traffic. But their job actually can be pretty simple, right? They can look at some traffic. They can look at, let's take a packet, right? As it's going through the network, right? All that switch should be doing, or all that it's really good at, is looking at that and figuring out where to send the packet next, right? So we've got memory in those blue boxes, right? Essentially lookup tables, right? Look at this, figure out where to send it next. All the logic, in other words, populating that memory, can be sort of lifted out of those switches, and if you sort of put it in, conceptually one place, that can be distributed, I should say, but logically we can think about that as being separate from the sort of brawn of the network that's pushing the packets around. Then we can start this very seemingly simple idea, right? Kind of obvious in hindsight. This is a huge game changer. Because if you think about what's going on the left, right, we've got our major router and switch vendors who are packaging software with the routers and switches, and you are basically stuck with what they're sending, and you've got this problem that I've been spending the last 5 or 10 minutes talking about, where you've got to go sort of do something individually to each one of these routers and switches. Well, now, let's assume I've got, and I won't spend too much time on the details of how that works, but let's assume that we've got a way of talking to the switch hardware, some sort of control channel, if you will, as I've shown with the dotted lines here. As long as we can kind of agree on what that control channel should be, now I can kind of do whatever I want up here, right? And actually this can be written in any language that I choose. So that's pretty cool, actually, right? Because I can now do, I can write a software control program in my language of choice. People have written controllers in just about, many, many languages. C, Java, Python. I'll talk about a domain-specific language in just a minute that helps us tackle a specific set of problems. But this has really changed the game. So you will hear about, you may hear about SDN or software-defined networking in various ways. It's one of these terms that sort of entered the zeitgeist so much that people just sort of try to retrofit it onto whatever they're already doing. But in a nutshell, that's basically the concept: is separate the control logic from the hardware, the routers and switches that are running the network, and allow us to control the behavior of that network from some logically centralized software program. Okay, so this is really changing the game. It has received a lot of attention in data centers. I'm not going to talk about data centers today because that's not what I work on. I spent a fair bit of time looking at campus and enterprise networks, so the first part of my talk will talk about that. Most of the work so far, including some of the work that I'll talk about in the first half of the talk, is inside a single network. You may remember from your networking course that the internet is in fact not one network, but it's actually many different networks. It's Comcast and Level 3 and AT&T and Google all sort of talking to one another. And the second part of my talk is going to be about how we're applying the concepts that I described to make those kinds of interconnections a little bit easier to understand, because that's another big mess. So in the first part of the talk, I'll talk about how we've been using SDN, building on that concept to design new abstractions for to help network operators both verify certain aspects of the network configuration, as well as cope with the dynamism that I talked about, the sort of fact that things are changing all the time. Then I'll talk about interdomain network traffic. Okay, so I'll start with a story. And I won't get into all there's a lot of sort of networking jargon on this slide, and I'll try to basically abstract that for you. But this particular story starts, 5 or 6 years ago, and the Georgia Tech campus network operators came to us and they said, we've got this problem of authenticating users on our network. We've got this really messy system. I'll describe to you just a minute how it works. A host connects to the network, right? So you bring your laptop or your phone or whatever. If you're someone in the dorms, maybe it's an Xbox or something, some kind of host, and you bring it to the network and you connect it. And the job of the network is to basically figure out, should this host be here? And if it should be here, what other parts of the network should it be talking to? So this is an access control problem, right? Okay, so the host connects, sends some kind of packet. Okay, so there's a bunch of acronyms on here, and actually, networking folks love their acronyms. And I think one of the things about SDN, I think that's if it has any impact, it will hopefully be to get rid of some of these acronyms. So I'm not going to explain to you all the details of the protocols here, but the next thing that this particular thing does is sort of figure out, a host connected. Have I seen it before? Like, what is this thing? And if it has the host registered? If it hasn't registered, it will basically say, it should be on this part of the network. Let's sort of move it over to this part of the network that registers the host. Okay, if the host successfully registers, then we're going to update some firewall configurations, make sure that traffic can get through to certain parts of the network. We're also going to scan that host to figure out if it's infected or not, right? Because if something's infected, we obviously don't want it talking to the rest of the network. Turns out the solution isn't perfect, but I'll come to that in a minute. If the scan is clean, shall we say, we say, okay, well, this host is allowed. Let's allow it. Let's update this magical thing, which basically puts it on a different segment of the network. And now the host basically actually needs to reconnect for various messy reasons that involve sort of how we map hosts from one part of the network to another. So that's kind of brutal because what that often basically requires is a reboot. Some issues. Well, some things to notice. There are a lot of events that just happen, right? A host showed up on the network. A host basically tried to register, maybe through a web portal. That was either successful or not. A scan occurred. The scan either turned up an infection or a vulnerability or not. Depending on all those outcomes, we might want to forward traffic to different places in the network, or quarantine that host, or do something. The other thing, of course, is that the state of the host might change, right? If it's a guest, their registration might expire. If it's a host of any kind, it might be uninfected now, but what about an hour from now? Well, then we got to do something. And remember that last step was we're going to move the host from this part of the network to another, so we're going to ask it to reboot. Well, that doesn't work so well when the host becomes infected and we want to basically move it back into the quarantine. So lots of stuff going on here, and basically, had the IT folks kind of scratching their heads or banging their heads against the wall, probably more likely, and saying, I think around this time, the SDN buzzword had sort of surfaced. And they said, this SDN thing, it can slice bread, it can it can do everything. So surely it can fix this problem, right? You guys go figure that out. So we said, okay, let's sort of figure this out. Just like anything, right? SDN by itself is not automatically going to fix anything. It's just a concept, right? It's just a way of sort of refactoring our control logic. And some people have sort of the general concept sort of tackled or sort of made possible certain things here, right? So I've talked a little bit about how we can sort of maybe move away from low-level commands and scripts, but we're still talking, mostly about general-purpose programming languages. I'll mention Pyretic when I get to the details, but distributed configuration. I think basically the concept I mentioned kind of addresses that a little bit, right? Because we can sort of we can envision what a central control program might look like. But these things sort of remain largely unsolved, right? How do we deal with dynamics, and how do we sort of have any idea that what we're doing is correct? Okay, so there'd been some good work, I think, already, even by some folks in people that are in this community. Nate Foster, for example, has done some very nice work, sort of raising the level of abstraction on some of these languages. Pyretic is a piece of work that he did. But these last two questions sort of still remained unsolved, and that's going to be these are the two problems that I'm going to sort of talk about how we tackled them in our work. Okay, so what was missing from the SDN story? Well. This notion of dynamics is as I mentioned, very important in networking, as well as this notion of, or this sort of desire to have some assurance that what's being deployed is at least going to do what's expected. Okay, so I think there's sort of there's sort of opportunities here to sort of jump on. Okay, and that's basically what we recognized and we started to think about. there are all kinds of different network events, right? And I sort of alluded to this when I gave the example. Here's the other aspect to that story, is that depending on, there are different events, but depending on what that event pertains to, the operator might react differently, right? So depending on whether that's a guest of the network or important person, an employee, or a high-ranking executive, you might want to actually do different things, okay? But here's the insight, right, is that basically what was going on is that network operators, they're sort of reacting to these events. And often, just as I described that example to you, I can describe it to you in words, and it's not super complicated, right? The protocols that sort of underlie that are unfortunately too complicated. But the story is pretty simple, right? We've got some things that happen in the network. And I can kind of describe what I want to have happen. So can we basically somehow encode that in a program? Well, hopefully. And that's sort of where we tried to basically go with this work called Kinetic. And here's basically the main idea, right, is that we've got a software program, and we want to sort of embed relationships between those events that can occur, those failures, traffic shifts, intrusions, etc., and how we want that program to react. Okay, so if we go back to sort of blowing up the earlier picture, right? So down in the bottom, those switches, networking folks, we often call that the data plane. Okay, the data plane you can just think of as forwarding traffic. On the logic side, we often call that the control plane. Okay, so here's that control channel that we had before, right? And what we want to have happen is when some kind of events happen, we want this program to basically say, the state of the world or the state of the network has changed, so let me update what I'm doing, right? And let me basically now tell the switches to do something different, right? And I want a good way to reason about that, right? Okay, so these are sort of the unanswered questions that we tried to go after in this work. How do we embed that sort of, how that program should react to these network events? And can we get some assurance that, when an event happens, that the program is going to change its behavior in a way that we can sort of, that we can kind of reason about? Okay, so this work that we call Kinetic, it's meant to rhyme with some of Nate Foster's work, frenetic and pyretic and so forth, but the name Kinetic is meant to evoke the fact that basically we're dealing with dynamics here. Okay, so what is it? It's a domain-specific language and control platform. It's embedded in Python. It's actually embedded in Pyretic, but I won't. We'll see a little bit about what it looks like when I get to the details. It helps operators create these control programs that embed these relationships between network events and how we want the program to react. There's some aspect of verification that I'll talk about as well. I think the story there is not entirely complete, so I'll tell you about the types of things that we can help operators verify, and then towards the end I'll sort of talk about some unfinished business. The approach is basically, as I mentioned, to sort of create a domain-specific language. The issue here, right, is that if you sort of look even at the earlier work in SDN, a lot of it is sort of the control programs are written in these general-purpose programming languages, or the controllers are written in these general-purpose programming languages, which is great. I mean, because it's great for software, people who know, who are programmers. But as we know, general-purpose programming languages are hard to, can be very hard to reason about in terms of, the properties that they do or don't satisfy. By now, hopefully you have some appreciation that maybe, the types of things that operators are doing, you don't necessarily need like a complete general-purpose programming language, because often all you're trying to do is, push some state into the switches and then change whatever state is in the switches for some set of events. And that's a fairly constrained operating environment. So we can basically design a domain-specific language that sort is meant to operate in that regime. We do this, we express those sort of changing network states in terms of finite state machine, which can get quite big, as you might imagine, and I'll talk a little bit about how we address some of those challenges. One of the things that we realized, actually, after talking to some folks in your community, was actually that the finite state machine encoding is not only natural, but actually in terms of helping operators express these things, but it can be mapped very nicely to certain kinds of logics that allow certain kinds of reasoning. So I'll talk a little bit about that as well. Here's basically how this works. We borrow some abstractions from another domain-specific language called Pyretic. And the key thing to know about that language is that, well, it's embedded in Python, but the sort of magic in that language is that they have this thing called a policy variable. And the idea of this, it's a special variable, and all it is basically, you could think of it almost like well, it's a function, basically, that maps a packet to one or more other packets. So you could imagine something like, if I want to encode drop, okay, then my input might be a packet and my output is the null set, right? If I want to encode a forwarding action, my input is the packet and my output is basically the same packet with a different, location in that particular key value pair. So that's what you can kind of think of what this policy variable does, and I've sort of told you now everything you need to know about the previous work, right? Is there's basically this policy variable, it's a function, it maps a packet, each packet to one or more packets. Okay. What we do then is sort of build on that we build these new constructs and functions to express policies that reflect the fact that network conditions might change, right? So we take these policy variables, you have an incoming packet, as I mentioned, you map that to one or more outgoing packets, and then when network conditions change, we just want to change that policy variable, right? Easy enough. So you could imagine, now if I just told you Pyretic's embedded in Python, you could imagine doing this whole thing, right, in sort of a, write an event handler, write some case statements, right, and then, reassign your policy variable based on, whatever those, those if-then check, those conditions are. Easy enough, except then you're sort of out in Python land, and checking becomes a lot harder. So what we did is we decided to sort of restrict it a little bit further and express, basically develop some constructs for encoding these finite state machines. So I'm going to describe to you like a super simple example, 2 states. You can imagine now sort of how this gets a little bit more complex. I'll make it a little bit more complex, but you can imagine this can get pretty big quickly. So here's a simple example to sort of illustrate to you the types of things that we can encode. You've got an intrusion detection system, or an IDS, right? And for a particular host, that host is either infected or it's not. Okay, so I've got a variable. I've got an event, I should say, basically, that might come from an intrusion detection system, right? Here's the beauty, right? If you think about how this happened, this would happen sort of in the conventional network that I described. Operator buys an intrusion detection system, drops it in the network, it raises some alerts, that thing shows up on some console, and now panic ensues, and someone goes and logs into a bunch of routers and switches and tries to do something to make it right. We want to automate that, right? So life is a little bit easier because we've got that logically centralized control thing, but we still need a way of encoding that. So we've got now basically a finite state machine that we're trying to encode at that logically centralized controller, and it can take in these events. So, for example, a type of event would be an event that would change the value of the infected variable. Okay, so that particular event, which is sort of encoded in, or the event is encoded is shown in blue here, might change in a variable called infected from false to true, and then we basically have another sort of internal state transition that's not shown in the illustration, but basically you can imagine what's going on under the hood is when that external variable, or that variable that can be triggered by an external event has its value changed, that triggers an internal state transition that changes the value of this policy variable from allow the traffic from this host to blocking it. Okay? Good. Okay, so here's where things start to get fun. There are a couple ways that things start to get fun. One is basically describe to you what happens for maybe one host, right? But obviously there's more than one host, so that we start to get a lot of variables and a lot of states. Here's one thing that we basically build into the language as well, is the ability to, if you had to basically write or encode a finite state machine for the network for all possible hosts, we're not really getting anywhere, right? Because who's going to write that down? You could maybe go back to your awk script and churn that all out, but that's not any fun. The other, of course, is that we've got a lot of states to keep track of. Okay, so the way that we do this basically is we define an abstraction that basically says, well, here's sort of an equivalent set of here's an equivalent set of flows, meaning like I'm going to say that all traffic that originates from a particular address, all that traffic should be subject to the same policy variable, right? So I'm defining equivalence classes, and I'll sort of say more about that on the next slide. But what I can say is now I'm going to define one finite state machine, and I'm going to say, well, we can sort of replicate that finite state machine for each of these equivalence classes. Okay, so that makes it easier to write this down, because I can basically write that two-state FSM once and say, well, anytime you see a new, in this case a new host, but in general, anytime you see a new group of flows, a new bucket, if you will, just create another instance of that. So that helps the problem of sort of how to help an operator express this concisely. There's also the issue of sort of state explosion here. The way that we deal with that is to recognize that often the many of the hosts may never leave the common or default state, right? So we don't need to basically store the FSM until the host transitions out of that start state. So that helps us a little bit as well. The abstraction that we put into the language that helps an operator sort of define, like, okay, well, this is a finite state machine, and I want basically one instance of this for each host, or I'll say each equivalence class, right, is what we call a located packet equivalence class. And I won't get into the details of the particular name, but the idea is basically what I just said, which is to say, okay, I'm going to say all hosts, for the example I just described, it would be source IP, not destination IP, but I would say all hosts that basically, or all traffic that's coming from the same source address, should be subject to the same policy or should have the same state. So then I can sort of define these groups in that way. So that's a little bit about sort of expressing the finite state machine. Now I'll talk a little bit about verification. Okay, so I think it's fair to say that basically there's a lot more work to do here. It's also probably roughly fair to say that before this work, there was essentially no work in the area of having an operator basically be able to say something about a control program and its behavior before they actually ran it on the network. So I think this is probably the first and maybe still the only work in this area. But this is by no means the last word. I'll tell you what we've done, and I'll sort of try to illustrate to you where I think there's more to do. I think one thing that I will repeat at the end is that there's a lot of work to do here. Let me now describe to you a little bit what we did and sort of what it looks like and how it works. Okay, so the verification process that we basically encode, or we sort of implemented in Kinetic, is a very specific type of verification. We're basically looking at user-specified or operator-specified temporal properties, right? So an example, and I'll sort of show you how we encode this, is an operator might want to say something like, if the control program receives an alert from an intrusion detection system that the host is infected, then I would like to drop all packets from that host, right? Or I would like to redirect that host's traffic to a site where they can download patches, something like that. If, I might say, if the host's registration process succeeds, right? If the host successfully registers on the network, then I would like to I'd like to allow it to send traffic to the rest of the internet. If the registration fails, I would like to only allow port HTTP and DNS traffic to the internal network. Things like that. The process is basically automated in the sense that the operator writes this program, and before it actually runs, we run the checks. And here's basically how that works. So on the left of the slide, I have an example Kinetic program. It's hard to read, but the details aren't super important. I don't want to sort of go through the syntax here. But at a very high level, what's going on is that for each of those state variables that I showed you in the cartoon earlier, we have basically a function that basically describes its initial state, the transitions that are legal, if you will, and the events that can cause different transitions, as well as functions that may be called when those transitions occur. The nice thing about the way that we kind of designed that, and we actually did that work, most of the work on the left, before we even realized that I'm not a formal methods person, so I didn't even know new SMV existed. And when we showed this to Cole Schlesinger, he said, "Oh, this is really interesting because it looks a lot like something that you could check with the temporal logic." And that's exactly what we ended up doing, was to basically say, okay, well, we can take this and we can actually do just a syntactic transformation. And that actually happens automatically in the tool that we've built. So we just translate into this the new SMV model, and then we allow the user to write these sort of temporal properties, and then we basically say, okay, does this program that you've written over here on the left, does it satisfy those properties or not? Okay, so we use something called, well, you know a lot more about it than I do, but it's called CTL. Someone, I think, maybe Cole, told me that no one ever says computation tree logic. But these are the types of things that that one can express, and some examples of how those eventually get expressed. Okay, so there are things. So these are the types of things that we can do. I promised you that I tell you what we left out, right? So one of the things we left out, or I guess where there's work to do, right, is I can tell you a lot about what's going on at that higher level control program, right? How the behavior that's going to change in response to certain events. I still can't tell you, even after all the work we've done, I can't tell you that you won't have loops or that you'll never have a dropped packet, right? Because I haven't told you anything about what's going on with the writes to memory. Right? And you can imagine that basically I've got, like I said, hundreds of switches, right? And what order are those writes coming in? How are those updates happening? And Nate Foster has done some really nice work in something called consistent updates that sort of reasons about how you update the what we call the data plane. But I think what I've described here and what Nate has worked on still remain very separate, right? It can sort of tell you basically how the behavior of our control program is going to change. And there's been some nice work in sort of figuring out how to update the switches in ways that bad things don't happen. But there's still a fairly big gap in sort of how you bring those things together. We did a little bit of usability evaluation. One of the nice things about a MOOC is you have a captive audience, people who at least nominally have to complete your assignments. So we can basically feed them our dog food and see what they say. So here's some demographics of the people who are kind of taking the class and completing the assignments. You can see a fair number of operators here. We asked them basically we basically gave them a program, and we asked them to basically, actually 3 separate assignments, and we basically asked them to do the same thing in 3 different languages. One is this thing called POX, which is as bad as it sounds. It's basically just a Python-based SDN controller, very simple type of thing. Pretty useful for teaching, but not really industrial grade. None of these really, I should say, are industrial grade, but fairly primitive and low level. Pyretic is basically it's a Python version of Nate's work on frenetic, which you may have heard a little bit about, and then Kinetic is basically the language that I've described to you that we embedded on sort of within that. Okay, so we asked people, which of these sort of did you prefer? People seem to, a fair number of people seem to like Kinetic better. Some people like the others, obviously. But I think basically this is encouraging. I think we're making some progress here. And I think one of the things that I wanted to get across is that you can make a difference here. I have no taste for programming language aesthetics. I really have no intuition for programming languages. Programming language design, and yet I think with a little bit of help and a fair bit of domain knowledge, I think we were able to really sort of make a fairly significant step here. I think for those of you who are listening, I think there's a lot of good to be done here. We need better abstractions, and I'll talk a little bit about that in just a minute. One of the things we did is sort of look at lines of code reduction. In the interest of time, I will just tell you that basically we looked at a whole bunch of programs that were sort of out there on GitHub, sort of standard, network, network operator types of things. And the lines of code were less. As we know, that's not always a good thing. And I'll come to that in just a minute. Things people liked. The FSM structure is pretty intuitive, I think, and it's also concise. What people didn't like, I think, and this is, I think, where there's still quite a bit of work to be done, is that the learning curve is fairly steep, I think. But I think that may be true with anything. I think the real stickler is the last point here, is that the program, like the Kinetic program, when an operator runs that, of course it's going to generate some errors. And that's good in a sense, because the errors were generated because some invariants were violated or the specification failed. And it's good that it didn't run on the network, right? That's a step forward because disaster in production was averted. But I think we've got a long way to go in sort of helping people still figure out, well, okay, this program doesn't satisfy the spec. Well, why? Help me fix it. As many of you who've probably designed these DSLs probably know, the errors that you get when things don't go as planned can be even more confusing than the general purpose language errors you get. So I think we haven't solved those problems, and the whole debugging and troubleshooting aspect of SDN is just a wide open area. Testing, for that matter, as well, still kind of remains wide open. We deployed this in a couple places. I won't talk too much about that. Here are a few takeaways. This was a domain-specific language we built for this specific purpose. It took us a long time. 2009 was a long while ago. But I think we're now sort of at the point where we've broken through that initial wall. I think we really kind of understand where some of these interesting problems are, how to make next steps. This is all open source too, so I would love it if some of you took some interest. If you found this interesting, to sort of build on it, on what we've done, because I hope I've also convinced you that there's a lot of work to do. And here are some of the things, of course, that I mentioned as well. There's another topic I wanted to sort of talk about, as I mentioned, which was this problem of delivery of network traffic in the wide area. Okay, so I've labeled the networks in a fairly mundane way here, but this is a toy cartoon picture of the internet. Number 1 you might think of as Comcast. Number 6 you might think of as Google. In reality, they're probably more directly connected, but basically there are something like the internet, as we'd like to think of it, is actually 50,000 or more. It keeps growing, actually. I have to continually update this slide. 50,000 or more independently operated networks, all kind of doing their own thing, and they sort of cooperate. And as we know, most of the time things work out, and sometimes you get interesting failure or other kinds of scenarios. If anyone watches John Oliver, you probably saw the whole Comcast Netflix spat. That's just one example of where things can go wrong. There are others, as you may know too, where just routing goes incredibly awry, either for mistake reasons or for security reasons. This talk is not about security, but I could give a whole hour on that as well. Okay, so let me just ask you to bear with me for just like one slide. There's I warned you that we like our acronyms. The protocol that connects these clouds together. We also like our clouds. The protocol that connects these networks together is called the Border Gateway Protocol. It's, I think, fair to say that the protocol that most networking people love to hate. It's produced a lot of papers, and yet it's still there. And yet it basically works. And yet it works, but we'd love for it to work better. Okay. This glue that holds all these networks together, we'd love for it to be a little bit more flexible. And one way we'd like for it to be more flexible is right now the decisions that get made about how traffic is forwarded, they're really only based on where the traffic is going, right? Not where it's coming from. So you might actually want to make a decision not just on, oh, this traffic is going to Netflix or Google, so I want to do something with it. But actually, well, this traffic is actually going to Google, but it's from Pittsburgh, or it's from China. Maybe depending on where it's coming from, I want to do something different, right? So maybe I want to customize the routes by application, or by sender, or maybe even by application, right? Maybe if it's video streaming traffic, I want to do something different with it, send it along a better provisioned path. Another thing that actually is tricky is in that picture I showed you. It's tough for, say, someone who's on one side of that, that group of clouds to influence what's going on in sort of a, far off network. You can really only influence what your immediate neighboring network is doing. And then the mechanisms that sort of operators can use to influence the sort of the way traffic is forwarded. I'm not even going to bore you with all the details there. If you thought the Georgia Tech access control example was painful, the ways that operators do this kind of the influence traffic selection is even worse. And worse than being enough to make your head spin, it's incredibly indirect. So you can make a change, and you might think that, oh, I made a change. That's actually going to change what this neighboring network is going to do. That's going to change the way traffic is. Well, sometimes not even. Okay, so you can sort of make a change and hope for the best. So this is bad. And it's also very difficult to introduce like new things into the network. So if I want to basically introduce a load balancer, I want to introduce something that does, codes my video down to a lower rate, or I want to throw in an intrusion detection box or a firewall or something, it's actually tricky to do that. Here are some things we'd like to do. So wish list. Could we peer or could we connect to one another, choose where I send traffic based on the type of traffic it is, right? So if it's video traffic, maybe I want to send it, over my, direct, expensive, well-provisioned link, and maybe if it's bulk, email or whatever, I want to send it a different way. Denial of service, it's, a well-mowed topic, but it's still a big thing. There's a lot of denial of service attack traffic. Because of what I mentioned about influence, it's tough to basically influence anything but your direct neighbor. Let's say I want to basically block this attack traffic close to the source. That turns out to be pretty tough. Other things too, load balancing, right? So sending half of if I've got a destination, if I want to send half of it on one path and half of it on another path, that's actually sounds easy, but the current protocols make it tough. Other things as well. I'll talk a little bit about the last point in my coming example. What can you do with SDN? You can do a number of things. So instead of just matching on destination IP address, you can actually, the switch can actually look at other things in the packet header. So you could match on source and destination and make a decision based on that. Or you could match on destination and what we call the port number, which you could sort of roughly think of as the application type, right? To a very rough approximation. So you get a little bit more flexibility there. You could, as I've already mentioned, you can control entire networks with a single program, so that allows for some coordination, potentially even across multiple. This notion that those 50,000 networks should have any coordination is pretty foreign still, but I think SDN actually makes that closer to reality. Direct control over packet forwarding, and sort of a much wider range of actions. Okay, so what we started to do, and this is actually pretty real, and I'll at the end again I'll sort of mention that we've got work to do, but what we've started to do is deploy this thing that I talked to you about before, this concept of SDN. We've tried to deploy it at what are called internet exchange points. And these things actually are popping up like weeds all over the internet. Let me sort of show you what these things look like. So you could kind of think of it as like a conference of sorts, right? A bunch of networks come together in one place, and they sort of figure out like who wants to connect to one another, and they basically make their connections, and they do that. Okay, so they decide who wants to exchange traffic to one another, and they make those arrangements. Oh no. I was just getting to the good part. Is that real? I'm almost done. I guess we have to leave, huh? Exchange points work, and there we go. Oh, right. Essentially what happens is basically all these folks come in, these independently operated networks, they connect to a switch, and they decide who wants to connect to who. But of course, pairwise, that has scaling issues. So people do this through sort of a coordinator called a route server. And this is sort of how IXPs have been architected for the last 20 or 30 years. As I mentioned, there are a lot more of these IXPs now. And what we basically we make a conceptually very small change, which is to say, well, let's make that route server, let's turn it into one of these SDN controllers. And let's assume that switch that's sitting there is capable of speaking these sort of control protocols that I've been talking about. So there are a whole bunch of, there are a whole bunch of different, we're back. There are a whole bunch of different applications that are possible, and of course I don't have time to talk about all of them. So I'll just talk about one specific thing, which is basically what network operators like to call inbound traffic engineering. That's basically a fancy way of saying I want to control the way other people send traffic to me, inbound into my network. Okay, so if I'm, AS would be autonomous system. That's just a network, basically. If I'm network C, right, and I've got two routers connected to that switch, I might want to say, well, let's take my port 80 or my web traffic, right, or whatever's going over 80, and let's send that in port C1, and let's send everything else in in via port C2. That actually turns out to be really difficult with BGP because BGP is not so good at sort of working with ports. But But with something like SDN, that becomes a lot easier. And I've sort of, this is a toy, right? But you can sort of, the way that a lot of SDN works is you can just basically match on some fields in the packet header and then decide to take an action based on that. So this is one example of sort of where the fine-grained forwarding nature of SDN makes something possible at an exchange point that wasn't possible before. Building this turns out to be challenging. I have even less time now, and I wasn't going to talk about many of the sort of systems challenges and networking challenges, but I wanted to focus specifically on just what kind of abstractions do you give to operators, right? So you've got ASs or networks that are coming in. Each one of them basically wants to write a policy, but they're doing this independently. So how do you basically expose the right abstractions? And the abstraction that we chose to design was basically, we call it a virtual switch abstraction. The idea is basically that each one of these participants, A, B, and C, gets the appearance that they're directly programming that switch. So it's basically an abstract interface. So each one of them sees a virtual switch. Right? And that virtual switch, they sort of have the appearance of sort of complete control over, in the sense that they can write policies for it. And then the trick basically is, how do you combine the policies of each participant? And the way that we do that, I think the sort of closest analogy here might be, it's almost like a symbolic execution, right? You sort of take a packet that has certain header fields, and you say, well, what's going to happen to that packet when it hits the switch? Well, it's depending on what port it's going to come in, it's going to be subject to one participant's policies, and depending on what basically happens to that packet, it's going to go to another participant, or some other, it's going to go somewhere else in that switching fabric, and that's going to determine what policy gets applied next. So we can sort of take individual packets and figure out what the appropriate sequence of composition is to sort of apply the policies that each participant has written. Fortunately, there's been some nice work in this area, actually, by Nate and Dave Walker and others on sequential composition that made this sort of very easy for us to sort of think about. I just wanted to briefly mention as well that this is a real thing. We're actually basically, this is being deployed in a couple exchange points, some existing, some pilot, etc. But even in this area, there's like a lot to do, and I sort of welcome ideas, collaborations, etc. If this is exciting to you and sort of helping network operators and sort of building things into real networks is exciting to you, there's huge opportunities here for languages. I think we really haven't even started to think about the right abstractions. Quality of service, right? How do I prioritize a video stream over everything else? How do I send that down a particular path? Middle boxes, right? So things like video transcoders and firewalls and load balancers. I might want to say, send a particular application's traffic through that sequence of services. That's something that we don't even really know how to do, let alone write into a program. Verification is something that I talked about already in terms of consistency, but also the security properties here are pretty interesting and complicated. I don't have much time to talk about all of them, but you can imagine in that picture where we've got independently operated networks all coming into a switch. You've got access control problems, you have delegation problems, you have questions about where traffic should or shouldn't be allowed to go, and so forth. And then there's the whole question of measurement, right? We like to know what's going on in our network, so if something goes wrong, like we know about it so that we can fix it. But the primitives that we have to measure our networks are still incredibly primitive, and there's a lot of work to do, both in terms of the mechanisms, which I think our community is working on, but as well as just simple things like, can I write down queries in ways that are sort of easy to understand? That we're still very far from that. So I'm gonna actually end there and sort of leave this up and take a few questions, because I think this provides a lot of food for thought as far as opportunities that still remain. I think one thought I wanted to leave you with is, as I mentioned, I don't think I'd be standing here in front of you if SDN hadn't come about, because these problems were just completely intractable in the ways that networks were being run. Now we have this tool, right? We have this SDN concept, right, which basically allows us to write these higher level programs to control networks in these ways. And we've explored, and I've showed you today a little bit how we're sort of looking at access control on campus and enterprise networks, and how we're sort of starting to think about interconnection, like how ISPs and networks connect to one another. But we're really we're still in the very early days, and I think there's a lot of opportunities here for our communities to talk even more than they are. Some of those discussions are happening, but I think we have a lot more to talk about. So thank you very much, and thanks for coming back after the alarm.
We can take some questions. No, everybody forgot their questions. One step